Hello. So in this video, I'm going to show you how to increase the speed that you learn hardware design by a factor of up to 10 times. So instead of spending about 3 to 6 years learning PCB design, or it seems like it's taking forever and you're still not confident in your printed circuit board design skills, no matter how many boards you do, and then you get a new board and you're still not quite sure how to modify that, instead of going through all that anxiety and all that stuff, I'll show you how you can shortcut the process down to 3 to 6 months. So if you want to understand this new framework instead of the current way you're doing things, especially how I spent like 8 years to become a professional hardware design engineer, I'm going to show you how to do it in 3 to 6 months. Okay, and this is the new framework that you want to use to save yourself a ton of time. So watch till the end of this video. Okay, so how in the world do you actually take down the time from years to months in learning printed circuit board design at the professional level? The typical process that I went through, I started off in 2012 learning printed circuit boards in order to keep my job. I didn't know where to go. I looked for PDFs, books, and in around 2013, I came across the first online course. It was on Fidevel Academy for printed circuit board designs, and it was a 6-layer board, power electronics, and Altium Designer. By the way, this video is sponsored by Altium. They sent me this cool shirt. This is how I got this cool shirt, and yeah, check out their website and check out the link in the description below and click on it, because there you can access and get a free trial of Altium, and also click on the link on the side here where you can practice using Altium to design a printed circuit board from scratch, where I teach you on a principle-based way in how to design your own PCB. Okay, so check that out. And also, if you're looking into buying Altium, if you really wanted to go pro, then you get a discount from that link as well. All right, so thanks Altium. Now, 2013 to 2016, I had gained experience in power electronics design for printed circuit boards and also gotten into design for manufacturing for PCBs. Before then, my first little rinky-dink PCBs were 2-layer, copper clad only, no silk screen solder mask, like milled out on the CNC machine. I was also a CAM engineer on the CNC machine for my university, and you know, I was proud of those first boards, man. You know, the first 3 didn't work, but you know, the 4th one sort of worked, and the 5th one and 6th one did. Okay, 2016, I was designing power electronics and analog boards, still 2-layer. I hadn't gone into 4-layer yet, but they had solder mask, silk screen, and all of that stuff. And I was also mentored by a PCB design professional a little bit. Okay, for I'd say about 2014 to 2018. Okay, as a graduate teaching assistant. This time though, I was a control systems engineer for my research in college. I think I was in my master's or PhD at the time. Yeah, PhD. And so I'd gone into power systems. I was learning PCB on the side still. More courses had popped up. Oh, by the way, in 2017, I published the first course on Udemy for printed circuit board design. Okay, now the reason I'm telling you all this is to show you that a journey that I took and a journey that I found that others have taken to finally get to a point where they feel they feel kind of ready, but not fully confident in their PCB design. There's always some of that doubt. And some of us never make it. So to 2018, 2020, I'm learning more about PCB design. I had a failed interview for my dream company, and it just like really took it out of me, and I felt that, man, I'm never really gonna get good at this thing. So I took an 8-month break, but I decided to get back into it because I didn't really want to be in electric power systems anymore. I wanted to do hardware design engineering as a profession, and to secure my future a bit more in this new skill, in this new field. So I started learning as much as I could about signal integrity, EMI, so on and so forth. And now fast forward, I have taught students at my academy, Hasofu Academy, and how to design their own printed circuit boards, going from a different industry like hardware test, validation, quality engineering, from zero to to proficient and hired in on average 6 months, okay? 100% success rate. So instead of taking the years that I did, the like 8 years that I did to be able to become a PCB designer, it consistently takes my students about 6 months to go from 0 to hired. How in the world do I do this? So this is the framework that I'm going to show you and how you can achieve this as well. The problem with the path that I took, even though that's a typical side learning path, or if you happen to land in a job where you are supposed to be a hardware engineer, you spend 6 to 8 months maybe learning on the job, 40 hours a week, and then you're kind of ready because you learn from other engineers. That path left me with a lot of anxiety and a lot of doubt about my printed circuit boards and my hardware designs. I was never quite sure that they would actually work. And also, learning from the different courses that came out online, I could do those designs and those were all fine and good, and I could use rules of thumb to make sure I did the same designs properly and correctly, but I realized that I had become a copy-paste engineer. I could only do designs I was taught, not my own or new designs. I just, So what I want to show you is that there's a way to avoid becoming a copy-paste engineer or the anxious hardware engineer who's always doubting whether the board is going to cost the company money because you made a mistake, or you're afraid that it's going to cause the client to get upset with you if you're trying to freelance as a hardware engineer. Okay, I'm going to show you how I became a confident, complete hardware engineer, where I could look at any design and see what changes need to be made, and also how that board came about, or if we were to make changes, how to do them without needing guidance from like a book anymore or something like that. So here's the new framework. So here we go from the rules of thumb, right? Rules of thumb, or ROT, if you want to call it that. Just rules of thumb. Doing designs that already exist, and you just do them and you get them out and you copy paste and blah blah blah, to now what I call the mesh method to PCB design. It will organize things and bring clarity for you when it comes to printed circuit boards, a design, the whole spectrum, the whole gamut. And then there's a deeper layer to that, to where you can automatically understand and become a complete hardware engineer. You'll automatically understand what you need to do in order to design your own hardware from scratch and to modify any hardware design you want. The new way to understand and learn PCB design is to learn and understand the problems in physics, the domains in physics, when it comes to PCB and hardware design. We are trying to design a product that is subject to the laws and rules of physics in our physical domain in the universe. So we have what domain of physics? Mechanics to deal with. We also have, and then this is the the M. The E is for electromagnetism. T refers to thermodynamics, so heating elements and all that stuff, parts getting hot. And our last domain is time. Now there's more to PCB design and hardware design than just this, but this captures the bulk of it. So when you're a design engineer who can understand the challenges and problems brought about by these domains of physics, you will become a better hardware engineer. But this is the first lowest, deepest layer. So how does this play out, right? The problems that we have in mechanics for our board coming to fruition, right? The problems we have in mechanics, this comes with component spacing, right? Are the components too close? Are they too far? Is the mechanics materials? Are the materials we're using, the dielectric, do they have the right dielectric constant? Okay, the fabrication, when we put the PCB together, these are all these issues. There are all these mechanical issues that we need to solve. Then electromagnetism, this is signal integrity. This is signals, right? Propagation of signals, EMI, and other phenomenon, electrostatic discharge, ESD, and then you have thermodynamics. So we have heating, cooling, harsh environments, right? Entropy, so on and so forth. And then you have time. This is where we have components and chips. The SRAM, SDRAM, right? Is the RAM communicating quickly enough with our MCU, our controllers, okay? And this is where the problem of time needs to be solved. We need to sync these up so that these communicate as fast as they're communicating. We need to sync them up to make sure that they latch and get the data correct, okay? The hardware engineer who can integrate all of these into their understanding becomes the complete, confident hardware engineer, or the CCE, complete, confident engineer. The solutions to all your mechanical problems when it comes to fabrication is what we call design. This is engineering. When we engineer and create solutions to these problems, we call it design for fabrication issues. Design for assembly issues. Design for assembly deals with spacing, space. Design for fabrication deals with the layer stack up, the PCB materials, the etching, right? Design for test deals with spacing as well, and probes. Design for cost has to do with part selection. So, how easy or how difficult is it to place these parts and to source these parts? Generally, design for manufacturing. Manufacturing is a mechanical issue. I mean, it's also a cost and budget issue, but there's a lot of mechanical things going on. Is this design for manufacturing? The design is the process of finding solutions to these problems in physics for our PCB product. Here, I mentioned this is the MET, right? MET method to PCB design: mechanics, electromagnetism, thermodynamics, and time. The solutions to the problems, to the MET problems, I called, right, MESH, manufacturing. For the most part, manufacturing. What is E and S? E and S stand for the solution to the electromagnetism problem is designing for electromagnetic compatibility and designing for signal integrity. This is the ES, okay? And all the problems that we have in signal integrity, like crosstalk, designing for crosstalk, these are solutions to problems in signal propagation, electromagnetic interference, and ESD and all that stuff. So you have crosstalk, return path checking. We also have signal reflections. Solving all these problems, you're designing for signal integrity. This is the field of electromagnetism. This is the ES part, okay? Thermodynamics, you tend to deal with heat when you're dealing with high power. So there's actually more to this acronym. There's MESH, PIT, or I call it MESH PIT, right? Where you have power integrity. Power integrity. Solving power integrity problems helps you deal with heating. So you might use a heat sink to deal with a heating problem. You might use spacing and adjustments to where you put your analog, your digital, your power traces, your switching nodes and all that stuff. How you space and manage those affect how you route your part placement. Your part placement affects the design for assembly. Okay, I won't get into how they're integrated yet, but mind you, power integrity. So we're dealing with ground bounce as well, and signal integrity, ground bounce. Rail collapse, which stems from also signal integrity issues and whatnot, but yeah. okay, power integrity, and thermal performance. Okay, so that's how we get the PI in there, and the thermals. And then what's this H? H stands for the solution to the timing problem between components communicating with each other. Do you know what the solution is to the timing problem? We call that, as engineers, designing for high speed. Okay, so we're designing for high speed. Usually these are digital devices or high frequency analog devices, but we'll just call it high speed digital design. Solves the timing problem. Oh, and I'll just erase this and call this manufacturing. Manufacturing, you'll also see this labeled as excellence, design for excellence. Right? The understanding from a physics perspective, if we understand the problems, as deeply as we understand the problems, we know whether a solution like checking for crosstalk or return path checking or reflections, we know that if that solution applies to the domain of electromagnetism, if there's an electromagnetism problem, then we know we need to look in signal integrity, EMC, EMI reflectance to solve that problem. If we know the problem is a timing issue, then we know to look at high-speed digital design rules or principles and solutions. If we know that solving a problem over here or solving a problem over here in high-speed digital design works, but we're also aware that a manufacturer or a fabrication process can only do so much in terms of trace width, in terms of component placement. We know that while we do solve problems here, we might have a design for manufacturing issue. And in doing all this, we could have all of these right, but we may not know how to design our power supply or where to lay them out properly, and they might have too much noise, right? And so now you've done all these designs good, but then you find that when you pull up, get the board manufactured and made running, there's a lot of noise inside the design. Okay, or you find that you can design your board for high speed, for power integrity, for signal and crosstalk, and all of those are fixed, but around the 200th board, right? The 200 board that you ship out to customers, they start failing. Every 200 boards there's a failure. There's some capacitor that came off. Because it wasn't designed with the right standards for reliability. Okay, from mechanical reliability. So it's the engineer who understands all these frameworks and how they work together that allows him to be him or her to be a confident, complete engineer in hardware design. Understanding the categories, the physical categories in physics, and then the solutions to these problems. The moment you can understand the problem, you know what kind of solution you need to implement from this framework, okay? And also, just because you know signal integrity doesn't necessarily mean you know how to make a board that can be manufacturable at cost, right? You have to take cost into consideration. And all printed circuit boards are at the mercy of the manufacturability, the cost and reliability of the product, and the testability. What if you can't test to find that maybe your electrical rules, your E-rules, weren't adhered to in the original design, right? But I won't even get into that. Let's say you know how to design for signal integrity, handle reflections, you know how to do power electronics, power integrity, you know the design for manufacturing rules to make not till the millionth board fails mechanically, but you just route the traces and you don't do the proper length matching, okay? Or impedance profile, and also impedance. Oh, and this deals with stack up selection. And in your impedance profile and impedance control, right? It applies to both of these. Let's say you do all these things, right? But you don't know how to do the length matching for the timing. And in addition, you don't know how to do the length matching for the timing, or the layer stack up you should probably use to maximize the space needed for your routing topologies, your T-branch topology and all that stuff, to get all your components to fit on here and to communicate well. And so your RAM, and for your RAM to not go dead eventually, blue screen of death for some reason, right? You can have all these things, but still have a dead or glitchy board if you're missing that. And the thing is, if you're trying to learn high-speed digital design and you don't have EMC and signal integrity as your base, then that's going to be a tough road if you try to design or fix any issues in your high-speed digital design, because these are highly dependent on your signal integrity. The whole board is highly dependent on the manufacturability. And then there's a power integrity. All devices need optimally clean power in order to function well. So how are you going to route and put out the decoupling capacitors, right? To deal with that noise, to avoid ground bounce and rail collapse, okay? And your overall impedance profile, okay? This is the framework that you can use, that once you understand and build your base in each of these topics, high-speed digital design, power integrity, EMC, signal integrity, manufacturing for design for manufacturing. Once you think in this way, putting information in these buckets, all new courses, all new pieces of information, all information you've learned, all information you've collected, you can put it into these categories. Now, I know that I've excluded RF from here. That's an electromagnetism and everything, but I won't cover that right now. That's a whole other thing. And also, I know there's more in terms of thermal, but we're just going to leave that out for now. Okay, all new information that you gather and gain, it's not just some piece of new information that you have to sort of try to weave into something that sort of makes sense, and you have to apply it at some point in time in the future in a new design. But if you remember to pull up that PDF that you have it in your downloads folder, okay? So all new information you can categorize this way, and then now you no longer have to So now, because of the mesh, PIT, mesh pit framework, and the MET understanding of when to apply these solutions to your problem in the PCB design space, you can create your own rules of thumb. Rule of thumb 1, rule of thumb 2 in these conditions. The rules of thumb apply only to boards in specific conditions. Now, a lot of them are very useful, but they're useful for specific situations. It's kind of like using a formula. The formula only applies to the problem if the problem meets certain conditions. But how do you understand or know what the conditions are and when to apply or to not apply the formula? Knowing the conditions is how you gain the confidence in PCB design, and how you'll be able to design any new and innovative designs that you want, and also to be able to modify existing designs as well, and understand how designs are done. Just like how I analyze a design, I'd never done it before, but by Maxim Integrated, if you check that link in that video, I explain and I break down and say, okay, this is what they did here, this is why, this is what I expect to see based on these principles, and sure enough, it was the case. So if you want to check out the video on how I broke that down, I've never designed it before, but I understood how the layout was done and why, okay? Because I understood this whole framework, okay? So thinking this way will drastically reduce the learning time, okay? So how do you make this into actionable steps? Actionable steps. All you have to do really is gather your information in these different domains, right? Gather the information in these different domains. Get your books on signal integrity, high-speed digital design, power integrity, thermodynamics, and design for manufacturing, and build boards focusing on each one of these. In fact, you could work with one single board, maybe a FPGA-based board and whatnot, and forget about whether the timing and routing and tracing is done properly. Focus on design for manufacturing rules. You get your IPC 2221. right? You get your DFM guides. Check those out and then apply those rules to your design. Once you're done with that iteration, go on to the next one. Apply only the EMI and signal integrity rules to your board design, right? Rinse and repeat. Apply only high-speed digital design rules, length matching, impedance control, and all that stuff to your high-speed digital design. Repeat. Only care about, in the same layout, the power circuit in your design and see if it's laid out properly, and test it for power integrity analysis. And then finally, do the design again, but focusing on thermals, thermal placement, and thermal management, okay? If you do this, you will rapidly and drastically increase and improve your skill set and confidence when it comes to printed circuit board design. Do that as many times as you want, but I guarantee you will gain that confidence you might be missing or lacking despite however many designs you do. The reason the current method doesn't work as quickly is because we're getting all this information through different projects and everything in disparate fashions. It's kind of like doing different bodybuilding routines, right? You do 6, 7, 8 different bodybuilding routines, you get good at all of them, and eventually you become a great bodybuilder who's versatile. But if it's a new routine, you don't necessarily know if those exercises work for you or if they're safe, but you sort of have an intuitive feel of muscle memory of what feels right and doesn't feel right, but you're still not quite sure, and you don't know what you don't know. However, if you were to get taught anatomy, I guarantee you did a crash course in anatomy for 2-3 months, and then any bodybuilding routine you come across, any running exercise you come across, any swimming exercise you come across, you'll know from the anatomy of the body whether those motions are safe or if they're unsafe, or if they work for you, if designed to work naturally with the body or not. And then imagine understanding the foundations of anatomy, health, nutrition, all those core foundations, and then performing with awareness each of those new styles of exercises, each new bodybuilding program. You'll greatly accelerate your growth and development as an all-around athlete. Because in this day and age, in order to be hired, especially long-term, and to secure your future as a hardware engineer, you need to be an all-around mathlete, okay, engineering athlete to be able to handle this, what's in demand for today. Okay, so thank you so much for watching this video. I hope this brings a lot of clarity to why there's been that lack. There's this anxiety, the anxious hardware engineer syndrome, to designing your PCBs and feeling like you're always missing something. Learning your mesh framework, at least minimum your mesh framework, it will help close that gap a lot faster so that you can start achieving your dreams in hardware design engineering and making your own innovative products. Thank you so much for watching this video. If you'd like to start designing your own hardware, click on the link and book a call with me if you are serious about going the distance and becoming a professional hardware engineer, and if you want to ask about my bootcamp and coaching program. Okay, thanks so much for watching, and you have a good one.